Alright, dudes, here's what I'm thinking. I heard it through the grapevine that this class is really hard. Or at least that's what one of my other students told me that some of his friends were saying in class. What do you folks think? Do you guys agree with that statement? This class is like super hard or okay. Crazy hard. Alright. I would be fine with slowing this class even more, slowing down this class even more as far as like, as far as when assignments are due and whatnot. I kind of wanted to finish off with chapter 2 today and move on to chapter 3, stoichiometry, but I think that that might be a little bit like a little much maybe. So I think what I'm going to do is I'll try lecturing on this stuff today. Why don't we go over some of the homework problems with you folks today? There was that question number 10 where it asked for the elemental symbol of lead, and I put down Fe for some reason. I have no idea why, but it's obviously Pb. So I think that what I was thinking in my head was iron, because iron is Fe. Anyway, yeah, let's lecture a little bit on this stuff, and then we'll, you know what, today what I'm going to do is, for chemistry specifically, I'm going to go over, I'll try to just kind of go quickly through the lecture, and then really hit your questions that you might have. We cool? All right. So we talked about isotopes. Now, what an isotope is it has exact same amount of protons because you can't vary the number of protons. So we have different isotopes of this thing, which means it has a different number of neutrons. Because essentially, I think of an isotope as something heavier, as a heavier version of my element. And in this particular case, my element is, well, let's see. If there's 11 protons, that must mean that the atomic number is 11, which means I'm dealing with Na, which is natrium, more commonly known as sodium. One second, let me close the door. So, I have 11 protons, which means Gernsbaugh-Barons, I'm dealing with sodium, Na. If you look it up in the periodic table, you'll see a big fat 11 above the Na. And that's how I know what I'm dealing with here. However, one of them has 12 neutrons, and the other one has 13 neutrons. So this one is a different isotope of sodium. It has the same exact charge as this one. It has the same exact number of protons, it has the same exact number of electrons. It just has more neutral things added to it. So it's a heavier version of this sodium ion. Does that make sense to you? Or no, I shouldn't say sodium ion, I should say sodium molecule. Okay. So an isotope carries a different number of neutrons, and that's kind of really what comes into play here. Now, a covalent bond is a bond that is formed between between elements sharing electrons. I have a nice visual for this, but I think I should probably, I'm just going to go over this real quick. And I'll tell you what I'm going to do is I'm going to extend chapter 2 into next week. So what I'm going to do is, I think I wanted to wrap it up by this week. I'll tell you what, why don't we just take a look at it now? Let's take a look at your chemistry. I'm going over to the calendar here. And I have, let's see, chapter 2, chapter 2, chapter 2, chapter 3. All right, here's what I'm going to do. I'm going to take the chapter 2 stuff and I will move this back to tomorrow. Move this one out here. I know what I'm going to do. I'm going to take the chapter 3 stuff, push him back a week. Or at least a couple of days. And then what I'm going to do is I'll probably fill in next week with a bunch of chapter 2 review stuff. So we're going to go more into the periodic table and more into this other stuff. Sound good? So I'm going to go off the book in next week, and we're going to cover the rest of this stuff. Does that sound all right with you? All right. Because I feel like there's so much in chapter 2 that I want to cover that they go through it so amazingly quickly that instead of me burning through the stuff, I think it would be best if we go through it slowly. So let's talk about an ion, because an ion is really important as well. An ion is made when we have a different amount of electrons. So we're not talking about different. So there's two ways I can mess with a element. I can mess with the number of neutrons that I'm dealing with. And if I do that, then what I do is I create these isotopes, as we talked about before. Or I could either throw in or take out a bunch of electrons that I'm dealing with. And if I did that, then what we're dealing with is a ion. I think one of my favorite cartoons to kind of give me this concept is I lost an electron. Okay. I think one of my favorite cartoons is this little one right here. It's be like, yeah, this guy right here. I'm hit. I lost an electron. Are you sure? Yeah, I'm sure. I'm positive. You get it? Yeah? No? Yeah? Get it? Haha. Okay, right, exactly. Because if this element over here has a balanced number of protons and electrons, and then like you lose an electron, that means you have one less electron balancing out that one extra, or not extra, but that proton that you have. So now instead of a neutral charge, you have a positive charge. And what you've done is you've created an ion of that element. Now, you can't go around adding or knocking out protons because that changes the element completely. That changes it into a completely different element. But you can go around knocking out electrons or adding electrons. If you add electrons, that would become a kind of a negative element. It would become a negative ion. If you subtract electrons, that would become a positive ion. Now, if we have positive ions that are created, which means they lost an electron, we call that a cation or a cation. And then if we gain an electron, so we have a negative version of that element, then we like to call that an anion, A-N-ion. I don't know why we came up with those words or why cat has anything to do with being positive. Because from what I understand, cats are quite negative, but that's neither here nor there. All right. So, a certain isotope is X plus, contains 54 electrons and 78 neutrons. What is the mass of, or what is the mass number of this isotope? Okay. So, here's a little problem that we have. So we have 54 electrons and 78 neutrons. So I have protons, neutrons, and electrons. I have 78 neutrons, and I have 54 electrons. That must mean I have 55 protons. Why 55? How come 55? Right, because I have a positive, what do we call that? That's a cation. I have a positive cation of this thing. It's a positive ion. And so there's one more proton than there is electrons, because that should balance out to be one positive number. Now, if I want the mass number, all I would do is I would add these two numbers right here, 55 plus 78. And that should give me 133. Is that correct? Yeah, I think that's correct. 133, which actually this number was supposed to slide in. That's your answer. The mass number is 133. The reason being is because the mass pretty much always comes from just adding up the number of protons plus the number of neutrons. The electrons don't really add any mass, because remember, like, I think that an electron is like 100,000 times smaller than a proton or neutron. And we covered that before. That was last lecture. All right, the periodic table. I wish I had a periodic table to play with here. Let me go find one. This will work. Give me a second. Perfect. All right, let's zoom in. All right, here's my periodic table. Can you guys see that? Yeah, you're right, Cameron. I really truly apologize. Today was supposed to be the Pokemon game that I came up with, and I couldn't. Actually, it's not that I couldn't find it. I didn't put it online for me, so I'm gonna have to do that for you as a part of later on this week's assignment. Remember how I told you folks that? Remember how I told you that I'm going to expand Chapter 2 out and kind of push everything back, push it back so that the homework is due later on, and I basically go over more. I have more time to go over the periodic table and the reason why we're putting the periodic table correctly together. Well, that's the lecture. In that lecture, I'll cover the periodic table with you folks and that kind of stuff in more detail. And that's where I'm going to give you the Pokemon thing, because I think that's a really fun lab. Cool? All right. So here's the periodic table. Here's the real periodic table. Now, we separate the periodic table into metals versus nonmetals. And we also set them up into groups and families. Now, the groups would be the vertical columns. So this is group, here's group 1, here's group 2, here's group 3, group 4, group 5. Those go vertical. Cool? And then the periods in this thing go horizontal. So here's period 1, and so on and so forth. Period 2, period 3, period 4, period 5, period 6. Are we cool with that? All right. Now, the metals would be actually, the metals is everywhere on the side of this little staircase line over here. So this is a little staircase line right here. That's actually all we got. We don't necessarily know about these guys over here. So the metals is everything to the left of this staircase right here. So aluminum is a metal, germanium is a metal, gallium is a metal, antimony is a metal, that kind of stuff. There's a really interesting metal that's around here, like this guy, and that guy has a lot of weird properties because that's actually a transition metal. Now, over here on this side, these aren't metals. They don't come as metals. This guy in group number 18, this guy is also known as the noble gases. And you know what? I really want to do that Pokemon assignment with you because I think that would be super helpful when doing all of this stuff. So I'm just going to kind of briefly go over this stuff, and I think that might be my lab. Is I might have you folks. I hate to do this to you, but I think that the best thing to do for lab this Wednesday coming up is we might not do a lab. We might do arts and crafts, which is not to say don't come in, because I'm actually going to have you build things and build models and those kinds of things, which is really interesting. But yeah, I think that's going to be required that we do this Pokemon game on Wednesday as our lab. That would be a good idea. All right, so here's my periodic table, and I told you about gases and metals, and let's see, what else do I want to tell you about this? Groups and periods. There's the thing right there. All right. Let's talk about naming compounds and naming different elements and being able to name these different things. What we do is these elements over here, this element right here, it likes to form what we call a cation. It likes to lose one electron if it could. If it can lose one electron, these guys like to do it. So they react a lot really well with other things because they want to get rid of one electron. So they usually, anything in group 1, they like to form a +1 cation. Does that make sense to you? Or lithium. Lithium likes to form a +1 cation. Things in group 2, like magnesium, they like to form a +2 cation. Is hydrogen a metal? No, hydrogen's not a metal. That line actually kind of comes over here. Lithium and beryllium can be thought of as metals. Yeah. Okay. Let's see. I'll tell you what. I kind of don't really. All right. I hate the way that this book explained it to you, and I wish I grabbed the Pokemon game for you. But let me explain this to you, Cameron. One of the things I'm going to teach you later on, this is probably what I'll be teaching you on Wednesday, is that I'm going to teach you how to draw out the shells of these elements. Now, for hydrogen, we usually draw that like this. Whenever we write hydrogen, we just put an H in front of it, on the inside, and then we put the one dot on the outside. because it has one electron, right? If you look up here, hydrogen has one proton, and a neutral element version of that would be one proton, or one electron. Does that make sense? Okay. So for helium, that's written pretty simply. He, that's my circle, but I have 2 electrons. That's right up there. All right. Now, for lithium, each of these circles can hold 8 electrons, except for the innermost circle. The innermost circle can hold 2 electrons only. So for lithium, we would write that as this. It would be drawn as this. Are we cool with that? So this second shell on the outside can hold up to 8 electrons, because the first one can only hold 2, but every shell outside of that can hold up to 8. Which actually, I think like the 5th shell holds a different number, but I can't remember that right off the top of my head. Okay, so check this out. The rule goes, let me get back to that. But the rule goes is that every element, what it wants to do is it wants to have its outside shell complete. So if ideally this lithium would like to have all of these spots full, its outermost shell full. But the problem is with lithium, he's got like one electron on the outside, and he's like, dude, if only I could get rid of that one shell or one electron on the outside, then I would be this. And his outermost shell would be full. Yes, exactly, Bradley. He either needs to gain 7 more electrons or just lose 1. Now, which would he rather do? Gain 7 or lose 1? It's harder to go out and find 7 things that he wants to gain. So what he'll most likely want to do is lose 1. It's less amount of energy that he has to deal with. So this lithium becomes a lithium plus 1. Because you lost an electron. So lithium loves forming a lithium plus 1 cation. Does that make sense? Which is why, for example, natrium, let's look at natrium, or also known as sodium. Sodium has 11 electrons to deal with. So I have Na, I've got my 2 out here, okay? That's my first shell can only hold 2. My second shell can hold 8. So I've got 3, 4, 5, 6, 7, 8, 9, 10. And then now I can't fit any more on this shell, so I'm going to have to go to this next shell. And that guy is going to hold just 1 more. So I've got an 11 to deal with. Sodium doesn't like that 11th one out there. It's all pissed off. It doesn't. It's like, dude, if only I could get rid of that one. So what it does is it gets rid of it. It kicks it out. It says, you're making my outside shell not be full, and that's what I want. I want my outermost shell to be full. So what I'm going to do is I'm going to say I'm going to kick you out, and I'm just going to be Na with 10 electrons, making it a positive 1 cation. Because in this case, it would have 11 protons and 10 electrons. Which is why Sophia is suggesting NaCl. I'm sorry, NaCl. Which is also known as salt. It's the table salt that you find on your table. Yes, exactly. Because if we look at the chlorine over here, because chlorine has the opposite problem. Chlorine has 17 electrons that we need to deal with. Let me draw it out for you. Here's chlorine. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. See, what chlorine is doing is on the outside-most shell, he has 7 electrons. What he wants is, he's like, man, if only I could fill up that one gap right there. Either I want to get rid of all 7 on the outside, or I want to gain 1. Now, what ends up happening is the sodium is walking around and like saying, oh man, if only I could lose 1 electron. And the chlorine is walking around saying, man, if only I could gain 1 electron. So the the sodium comes by and says, hey, we should work together. How's about this? The sodium comes along and says, hey, I can lose 1 electron, and you need to gain 1 electron. So why don't we do this? Why don't we take that 1 electron that I have, and I'll give it to you, and then you take that 1 space that you have, and you can have it. So for a period of time, yeah, they share an electron. And then so that makes the sodium happy, that makes the chlorine happy, and this is why sodium and chloride work, or chlorine work together. So whenever we're naming these compounds, first of all, when you name a compound, the cation, the positive, the one that naturally goes positive, it always comes first. So NaCl, that is known as sodium chloride. And what you do is, when I name this element, like when I want to figure out what the name is for this element, I would end the word with ide, I-D-E, if it's like the natural version that this thing wants to make. So sodium chloride comes from one Na positive cation and a Cl minus or negative cation, and those two come together to make a neutral guy. And so this is my cation, here's my anion, and so the anion is you end it with an ide if it naturally wants to lose 1 or gain 1 electron. Does that make sense? So let's try another one, like K plus I minus. Let me zoom out. I think my zoom is a little bit funny. There we go. Let's try another one, like K plus, put K plus I minus. All right, or Ki. So K is potassium, I is iodine. So if I wanted to name this, this would be potassium iodide. The reason why we need to come up with this crazy naming convention is because back in the day, chemists, there was no rhyme or reason as to why chemists named certain names. So that's why we have certain names like quicklime or Epsom salts or milk of magnesia or laughing gas or gypsum. Originally, some of this elements were called laughing gas or something like that, or salt. And it wasn't like, the word salt doesn't make you think NaCl. So what they did was they kind of came up with this solution where they said, all right, fine, there's going to be a certain naming convention that everyone has and everyone needs to learn. So that way if I say the name of the element, you know exactly which elements it's made of. Like here, I'll give you another one, and this one's a little bit weird. CaS. Okay. Ca is calcium, right? What kind of cation does it normally like to form? It normally likes to form a +2. Because it's got, remember, everything in this group wants to get rid of 1 electron. Everything in this group, it wants to get rid of 2 electrons if it can. So Ca, calcium forms wants to get rid of 2 electrons, so it forms a +2 cation. And then the sulfur is a 2-. So those guys come together and it's fine because this +2 cancels out with that -2. So what I'm dealing with is calcium sulfide. Does that make sense? All right, here's a tricky one. What about this one? Li3N. Okay. Lithium wants to create what kind of... Oh, am I doing your homework for you? Or is this like on your... No. All right. I'll tell you what, I don't mind doing some of this. I don't mind doing these problems for your, like, if this is part of your homework, this is kind of like the idea behind it. Okay. Lithium 3N. Lithium wants to create a +1 cation, right? So it's Li plus 1+. Are we cool with that? N wants to create a -3. So I'm going to need 3 lithiums to balance out with that 1 N, which means I would name this lithium nitride. Because it's normally nitrogen, but it's N3-, which is the natural, which is what N will naturally want to get rid of. Because everything in this column wants to get rid of 1, everything in this column wants to get rid of 2, everything in this column wants to get rid of 3 electrons. So that's how I would name it, lithium nitride. Are we cool with that? All right, let me try one more, and then I'm done with the class today. Go over 1 through 4 and a sample problem from 17 to 19. Those are super hard. Okay. Let me do this one, and then I'll go over something from what Bradley wants to do. So let me do aluminum Cl3. AlCl3. All right. Aluminum wants to gain 3 electrons, by the way. Or no, wants to lose 3 electrons. So aluminum, because you kind of, this guy wants to lose or lose 1 electron. This guy wants to lose 2. These guys want to lose 3. And then carbon and silicon, those guys are interesting because they're halfway, right? They don't want to lose 3, or I mean, what they are is they have 4 in their outermost their most shell. So carbon and silicon, they are fine with either gaining 4 or losing 4, as long as they have, I mean, they could do either or. So they can naturally exist as both a cation and an ion. But anyway, let's take a look at this. Aluminum naturally forms a positive 3 cation. Chlorine forms a -1 anion. So I would name this as aluminum chloride. Because I wouldn't have to give this a special name on this chlorine. All right, Bradley's saying 8 in the third ring, 8 in the second ring, and 2 in the first. Yes, the first ring can only hold 2 electrons. The second and third ring can hold 8 electrons. All right, class is over. I am done. However, Bradley, I will go over some of your example problems for you, and I'll keep that on the recording. Which ones did you want to go over? Which sample problems are you talking about? Are you talking about the assignment that's due today? Or was due today? Okay, let's see. All right, it looks like everyone hates 17, so why don't we go over 17? And then I'll do 1 through 4 as well. I'll take a look at it at least. I think that would be this homework set right here. All right. A sample of chloroform is found to contain 12 grams of carbon and 106.4 grams of chlorine and 1.01 grams of hydrogen. If a second sample of chloroform is found to have 30 grams of carbon, what is the total mass of chloroform in the second sample? Okay. So it's kind of like ratios, right? Like, let's see. It's kind of like H2O is water, right? And if I have, I don't know, if H2O naturally has 18 grams, where 16 of those grams come from oxygen and 4 of those, actually 20 grams. If I have 20 grams of water, 16 of those grams comes from oxygen and 4 of those grams comes from hydrogen. Right? Does that make sense to you? And I can actually look this up in my periodic table and whatnot. So if I told you something like, well, what if I had 8 grams of hydrogen? Well, how many grams of oxygen would I have if I still have water? Well, it would have to be 32 grams of oxygen, because you're just doubling this, right? Because I can't have some odd proportion. I can't have like 10 grams of oxygen and 8 grams of hydrogen. That would be a different proportion. It would no longer be H2O, which means you would no longer have water. Does that make sense? So what I'm doing here is I figured a ratio. I said, 8 divided by 4 is 2. So if I multiply this times 2, I should get my answer for that. So let's look at our chloroform thing, which I don't know the chemical equation for chloroform, but apparently for every 12 grams of carbon, you have 106.4 grams of chlorine and 1.01 grams of hydrogen. So if I'm ramping this up to 30 grams of carbon, how do I figure out the ratio of that I had to multiply 12 times 30 to get to turn 12 into 30? Well, my answer was I would just take 30 and divide 12, which is like, I don't know, it's like 2. It's got to be like 2.8 or 2.7, 2.5. Okay. So what I would do is I would multiply this by 2.5 and multiply this by 2.5, and I would get my number here. And then how much total do I have? Well, I would just add it all up. Is that what you guys did? Genesis, did you get it wrong? Or you did that and you got it wrong? Oh, okay, cool. Well, you got it right. All right. From the information in this chapter, the mass of the proton and mass of the electron and the size of the nucleus and calculate out the density of hydrogen. Wait a second. Is this the right? Yeah. This is the right one, right? This is what you guys wanted me to go over. Oh, I don't know what the answer is. I guess I could look it up. I got 299. I'll tell you what, I'll make the margin a little bit bigger. That's only fair. Yeah, that's what I got. I got 299. All right. Calculate out the density of hydrogen. Oh, I guess I didn't give you... Oh, this is the hydrogen atom and this is the hydrogen nucleus. Okay. That one's pretty straightforward too. I think that somewhere in the slides or somewhere in the book I told you the size or the diameter of an atom. And so the diameter of an atom is, I don't know, it's whatever it is. From the diameter you can figure out what the radius is. From the radius you could figure out the volume. You would multiply that by 4/3 times pi r cubed. So you have the volume of your hydrogen atom. You also know that the mass of the mass of a hydrogen atom, and a hydrogen atom contains 1 proton, 1 neutron, and 1 electron. So you can add those up and get the mass. And then to get the density, you would just do the mass over volume. Add up the masses of the proton, neutron, and electron, and divide it by the volume of 4/3 pi r cubed. And the same goes for the nucleus. It's just this time you're only adding up the proton and the neutron for the mass, and then for your R is going to be drastically different. Genesis, let's pretend that the diameter of a atom is 10 centimeters long, 10 centimeters big. Does that make sense? Let's pretend that you found it in your book, and the book says that the diameter of an atom, because I told you, look inside the book, and here's what your answer is. The diameter, all right, I'll do number 17 as well. But I'm going to cover this for Genesis. The diameter of an element is 10 centimeters long. So what I would do is, to figure out the volume, I would plug in 5 into here. So that would be 4/3 times pi times 125. That's my volume. Does that make sense? Well, because the diameter is 10, your radius is 5. The equation for volume is 4/3 pi times r cubed. R is 5, and so that's what I would do. The diameter obviously is not 10 centimeters big, but I'm just saying. What if it were? All right. For the mass, I told you the mass of the proton, neutron, and electron. I forgot, I can't think of it off the top of my head, but let's say this is like 4, 4, and 3, or maybe 0.2 grams or something like that. One's 4 grams, one's 4 grams, and one's 0.2 grams. Obviously, this is not the mass of actual proton, neutron, and electron. Well, in order to get the mass, you would just simply add this, this, and this. So your answer would be 8.2 grams divided by whatever you calculated in for the volume. That's how you figure out the density of an atom, of the hydrogen atom. And then the density of the hydrogen nucleus is, would just be, I gave you the diameter of this thing right in here. And then you would just do 8 divided by whatever. Does that make sense? All right, number 17. Which one's number 17, by the way? Is that it? Classify these as metals? What's the blue number? What is this number right here? That's my question. Is that number 17? Can anyone still hear me? Oh, okay. Yes, you can hear me now. Number 70? Oh, okay, 17 is 57. Got it. 57. All right, here we go. Write out the atomic symbol for each of the following isotopes. So A, Z, and X. Okay. So the number Z is 8. And the number of neutrons is 9. So let's see. If I remember correctly, this bottom number gives me the atomic number right here. That would be this number right there. So if I'm dealing with 8, if you look it up in a periodic table, wait, do we look at the text to find it? Oh, yeah. Actually, it's on page 54, by the way, Genesis, the information you're looking for. It's all on page 54. Okay. In your textbook on chapter 2. Okay. This bottom number gives me the number of protons. So 8 means I must be dealing with, I think that's oxygen, isn't it? Yeah. So that means this is an O. That's definitely oxygen. And this, wait a second, did I screw that up? No, I don't think I did. All right. And this number is 8 down here. This is the atomic number, and this has to be oxygen because if it has 8 protons, it has to be oxygen. If it had 9 protons, then you're dealing with fluorine. Or if it had 7 protons, then you're dealing with nitrogen. So this has to be an O over here. Now, what goes over here? Well, that would be 8 plus 9, 8, the number of protons plus the number of neutrons. So that would give you 17. Because really the mass doesn't matter how many electrons that you're dealing with. So for this question, I think you're supposed to type in an O over here. You're supposed to type in a 8 over here, literally. Oh, wait. For question B, give me the, oh, okay. So really, I think the answer for this should be O. Yeah, it's an O. Possible answer, O. Did you use lowercase? Is that why you got it wrong? Okay, Genesis, you're confused about question 11. Let's take a look at it. What's the blue number for question 11? I don't know. Yeah, so you just write down the symbol, O. Genesis, what's the blue number for question 11? It's number 53. All right, you said you got partial credit. Here's what I got. I got magnesium and then all of these. Let's see. Maybe you got one more that I did. All right. Anyway, that's my answer. All right. I hope that helped. I'll see you folks later.